everyone, welcome to Gate Pass. In this video I am going to take two problems which appeared in GATE 2012 and which were related to thermodynamics. So the first problem which I have taken, it was question number 30 in this paper, and it involves a very classic problem of charging of a cylinder. Okay, so let's go through this problem statement very briefly. So you have an ideal gas which is flowing through the supply pipeline at a pressure of PS, temperature TS, specific volume of Vs. Okay, it is used to charge a cylinder, okay, or fill a cylinder which is initially evacuated. Okay, and it is the gas is filled in this cylinder till the pressure in the cylinder becomes equal to the supply line pressure, that is PS. Okay, they have said that you can take gamma as a ratio of the two specific heats, Cp by Cv. If the final temperature of the gas in the cylinder is Tf, then you have to find out what is Tf equal to in terms of the gamma and the supply line temperature. Okay, so there are four relations which are given and you have to find out what will be Tf equal to. Fine. So this was briefly the problem statement. Now it's a very interesting problem because in most of the books which you refer to for GATE preparation, I have seen that this problem has been solved wrong. Okay, so let's go through this problem. It's very simple. In order to solve this, I am defining a control volume which is my cylinder. Okay, on this control volume I am writing my energy balance and material balance. Okay, so this is the simplified form of the general energy balance I have written over here. Okay, let's just simplify it further. Fine. So in the problem statement they have further said that kinetic energy you can neglect, potential energy you can neglect, there is no heat exchange between the cylinder and the gas pipeline. Further, since this is insulated, so there is no heat transfer between the cylinder and the surrounding, so Q you can take as 0. There is no external work which is being done. The only work which is there is the flow work which is absorbed in this enthalpy term. Okay, so the external work done is 0. Fine. Further, what you know is that there is only one stream which is coming in and there is no stream which is going out. Okay, so let's say that the mass flow rate of the entering stream is m dash and its enthalpy is h dash. Mind you that when I am defining the enthalpy of this stream as h dash, that means I am also fixing the enthalpy of the gas which is flowing through the supply pipeline as h dash, because these will be same. Okay, so now come back to our energy balance. Since there is only one stream which is going in with a flow rate m dash, delta H is, how do you define it? Enthalpy of the stream going out minus in. There is no stream which is going out, there is only one stream which is coming in. Okay, so now this thing gets simplified to your minus m dash h dash. Okay, and everything else is 0, so I am going to write it like this. So this is my simplified energy balance for this problem. Fine. Now this is my material balance. What does it say? It just says that the rate of change of mass in the tank. So T is for the subscript is for the tank. Okay. So rate of change of mass in the tank, that is equal to your m dash, that is the mass flow rate into the tank. Fine. This is your material balance. Very simple. Now what I am going to do is I am going to put the value of m dash from this material balance into this energy balance. So what do I get? D mu in the tank by dt, that is okay, minus instead of m dash I am going to put d mt, that is again tank dt h dash, that is equal to 0. Okay, now h dash is a constant because this is the enthalpy of the gas stream which is flowing in the pipeline. Okay, now what I will do is just take it on the other side. I can write it like this, integrate it with respect to time. Okay, then what do you get? You get something like this, delta mu of tank, that is equal to h dash times delta m of tank. Okay, now let me define that initially you have mass m1 in the tank and finally you have mass M2 in the tank. Okay, and correspondingly I am defining my specific internal energies initially with subscript 1 and final with subscript 2. So I can write this as M2 U2 minus M1 U1, that is equal to H dash times M2 minus M1. Okay, fine. So with respect to time, I am saying that initially the initial conditions are given by subscript 1 and the final conditions after time t is given when the cylinder is charged, it is given by subscript 2. Okay. Now initially you know that the tank is evacuated. So M1 is 0 to begin with. So in this case this term is 0 because M1 is 0 and this term is also 0. So what you are left with is you have M2 U2, that is equal to M2 H dash, or I can say U2 is equal to H dash. Okay. So this is a very important result which we have got and which will form the basis for solving this problem. Okay. So I am going to erase everything else and I am going to write just this thing over here. So what you have is that the specific internal energy of the gas in the cylinder once it is charged, that is equal to the enthalpy of the gas in the pipeline. Okay. Now you know that the absolute values of internal energy and enthalpy, it cannot be calculated. So we are going to define a reference temperature T reference such that at this reference temperature I have U reference which is equal to 0. Okay, I am just defining a reference temperature in order to calculate these quantities. Now for ideal gas, further I am going to write some relations which are general. Okay, you know that your delta U, that is equal to CV delta T. Okay, du is equal to CV dt, that's what I have written in integral form, and your delta H, that is equal to Cp delta T. Further you know that your for ideal gas you have Cp minus Cv is equal to R. Okay, so we are going to use these relations right now. Okay, so first of all I will write down U2 in terms of the reference temperature. Okay, so I am going to say U2 minus U reference. Okay, that is delta U, that is equal to Cv, and in this case when the internal energy is U2, your final temperature is Tf. Okay, so I am going to write Tf minus T reference. Okay, this is my equation number 1. Now let's write down enthalpy in terms of your reference temperature again. So what I have, H dash minus H reference, that is equal to Cp, and what is the temperature at which you have H dash, that is Ts. Okay, so it is Ts minus T reference. Okay, do you agree with me up to this point? Fine. Now since you have defined your U reference at T reference equal to 0, okay, then I can write my H reference in terms of my U reference. How? Because H is equal to U plus PV, so that's what I am going to do. So I am going to write H reference as U plus PV reference. Okay, let's say square bracket. Okay, that is equal to Cp Ts minus T reference. Okay, now since this is an ideal gas, PV reference can be written as R times T reference. So I can write this as R times T reference. Now what I will do is, okay, U reference is 0 by definition. So I am left with H dash, that is equal to Cp Ts minus Cp T reference, and I am going to take this on the other side. This is minus, so it will become of plus, so R T reference. Now R minus Cp, since T reference is common, what is R minus Cp? That is equal to minus Cv. So I can write Cp Ts minus Cv T reference. So my H dash becomes equal to this, and this is my second equation. Okay, but we have seen that u2 is equal to h dash. So I can equate these equations. U reference is 0. So your u2 is equal to this much. Okay. So I can equate this and this. Let's do that. So I am opening it at the same time. So Cv times Tf minus Cv times T reference, that is equal to Cp Ts minus Cv times T reference. Okay. Now these are same, so it will get cancelled. So what I am left with is Tf, that is the final temperature, that is equal to Cp by Cv times Ts. What is Cp by Cv? That is equal to, that is nothing but gamma. So gamma times Ts. So what you get is that the final temperature of gas in the cylinder, that is equal to gamma times Ts, that is the supply line temperature. So your option A is correct. In one of the leading books for GATE, you will see that this particular option has been given correct. Of course, now you know that this is incorrect. I don't know, they start with the work done and equate it to integral VdP. I don't know from where they got those equations. Okay, but this is definitely wrong. This is the right answer, and the answer which is given in the key provided with the GATE exam. Okay, so keep this in mind. This is how you should follow. Okay, so let's now move on to the next question. The next problem which I am going to take is question number 7. In this question, they say if the temperature of the saturated water is increased at constant entropy, the resulting state of water will be which one of them? Okay, so for that I have drawn a TS plot for you. Okay, so this is temperature, this is entropy, and this TS plot, you will see that it very much looks like your PV plot. Okay, so this is your subcooled liquid, this is your superheated vapor region, and you have again a bell-shaped curve up to critical point over here. This arm, this represents your saturated liquid, and this represents your saturated vapor. Under this bell-shaped curve, there is a liquid vapor coexistence region. Okay, the thing is this, what they are saying is you have a saturated water, so you are somewhere on this line, let's say over here. If I increase the temperature, okay, so if I make a straight line from here, if I increase the temperature, so in which region I am going? I am going in a subcooled liquid region. Okay, so the resulting state of water will be liquid. Whether it will be liquid vapor coexistence? No. Whether it will be saturated vapor? No. Whether it will be solid? No. Okay, so if you increase the temperature, it will the saturated liquid will become a subcooled liquid. Okay, so that was a very simple problem, and I would ask you to go and see your TS plot in your books. So thanks for watching, and if you like my teaching, please don't forget to subscribe to my channel and hit the like button, and thanks for watching once again.